So we are going to continue our how this we relate information for both exchange of information in terms of the distributions, the marginal distribution or conditional distributions, how this under an exchange, how things do relate. So the thing is that we should have so the mapping sometimes was one to one, but it was for arbitrary distributions. So we just try to do the same thing. How we can see that what I should say, we have to yet extend information for the we have not for the definitions of past distributions. So in order, if we assign measure to a set of variables, set of values of a random variable, set of values of random variable x, which is a simply positive number, then what I should say, so relative, what I should say, relative information vis-a-vis this random value, which sometimes also called as information measure. So we have to have simply assign a positive number ai to each xi in a finite case, and we define the probability relative to the information, probability vis-a-vis this relative to or relative probability distribution pxi relative to information measured to be yx to be p of x I log of p of xi p of I, which is basically expectation of which we defined previously. It's expectation of log of p of xi ai. So ai is the number of each xi. So this is how we can define this. So for a joint distribution with random variables x, so previously we took these individual elements of x and y and z, and then we could see how they could map to this individual. There was a one-to-one map. So here also we can have for a joint distribution with random variables with not information measures, not only ai, we can have ai, bi, ct. So thus we define total information relative to these measures as I, X, Y as probability of Xi, Yi, so on and so forth, log of P of Xi, Yj, Ck, sorry, Zk, and in the denominator now, not only Ai, we have these different Ais, Bis, and Ck. Now, so you can write this you will see as an expectation which comes out to be this expectation of log of Pxi, Yi, Zk, and Ei, Bi, Ck. So that the information measure on the Cartesian product is always taken to be the measure of individual. So the measurement of Cartesian product is taken to be measurement of individual information measures. Because so in the case we also said that if we are interested in the conditional probability, so what happens to other parameters? Things become oblivious to the parameter which we are interested in. And there is a statement which somehow will encompass this thing, is that the information of a distribution relative to a given information measure never decreases under refinement. So there can be proof to it also for several variables. So this proof has been attempted in the appendix, but the point, the main thing is so if we information distribution relative to the given information measure. So the the part of the information or related part of the information which becomes important for us, it's oblivious or it's having a disjunctive intersection with the other parts of the system, and religion never decreases under refinement. So it will come out to be same. So it will not decrease. So the thing is that if there are more than one variables, its effect will not show on that information measure which we are interested in. So now there comes also what I should say in mathematics, whether the information, relative information, whether we are interested in is determinate or indeterminate, or whether the information is discrete or in that sense continuous. So if it's so we have to have a probability measure. So we'll go take a bit use the language of Lebesgue measures, in which we normally talk of Lebesgue measure is how to identify those subsets or subspaces. So in that sense, so here, so those subspaces, whether they may be marginal distributions in the joint marginal or conditional probabilities in those joint probabilities which we have identified, and whose probability measure never decreases under refinement. So if you want to see how we can have, for example, how we can understand information computed with respect to uniform measure of, we have to understand information computed with respect to uniform measure for discrete distributions and Lebesgue measure for continuous distributions over real numbers. So in case of mixed distribution, the continuous density, which is P of x, y, so on and z, and discrete lumps, P prime, x, y, j, z, k. So we can understand information measure to the be uniform, or we can understand information measure to be uniform under discrete things and continuous under and Lebesgue measure under Lebesgue measure under continuous range. So the probability measure, if you want to write in terms of if you want to identify this xi, yi, zk log of, so for discrete measures, it's probability of xi, yi, zk. So this is discrete. For continuous, we are going to use integral because there is a continuous variation. The integral will vary along dx, dy, dz, and it may take continuous values on those subspaces which belong to these probability distributions x, y, so on, dx, dy, dz. This is continuous. And since in quantum mechanics, we normally, there are also, one is the pure thing case, and there are mixed cases also, which may belong to both these continuous as well as discrete spectrum. So the information measure, which we can find in those, whether it's continuous or, so we have to see. So if there are mixed cases, if the density matrix, so if we have both pure cases as well as in mixed cases in quantum statistical mechanics normally. So here, if we want to write these joint probability distributions, how we can find go for both discrete as well as continuous case for quantum mechanical cases, which may be mixed. And pure can be a particular case of mixed, then we can write it as P prime xi zk log of and plus, this is for discrete case and this is for continuous case. Z dx, so we have dx, dy, and dz, and so on. It depends on the dimensions. You can increase, if there are three, you can have dx, dy, dz. So it's for a mixed case, for mixed quantum mechanical case, we can have how we can have this information distribution and the probabilities associated. You can have the subsequent example is how we can see decay processes. Information decay in stochastic processes. You can use the language of information or the description of information theory, how those mixed states or mixed quantum mechanical states who can relate them to entities like entropy, and there can be seen. But here we'll just we'll do another example rather than concentrating on this one, which is that of conservation of information in classical mechanics. So if you have, again, we are going to see what I should say, the map of, in the simplest cases, position and movement coordinates in one space and position and momentum in the another space, and there is a joint probability distribution, and we have to find a particular way of finding a distribution where these random variables are related somehow. So if we have, for example, xi, yi, zi, pi, pyi, pzi, xn, yn, zn, this is pnx, pny, pnz. So this is phase space for all position as well as momentum coordinates. So invariance of measure, I major, can be written as implies that we are not interested in, if we talk in the language of classical mechanics or classical statistical mechanics, we will talk of phase space. Phase space becomes invariant under that Liouville's theorem. So we'll talk of, for example, information distribution, probability distribution in that phase space, such that the total I total can be given as IXI, YI, ZI, where we have PXI, PYI, PZI, so on. So this is simple variables. Now we can have variables IXN, YXN, ZXN, ZN, sorry, Y. The same with PXN, PYN, and PZN. OP can be like this, and so on and so forth, which is the joint distribution of all position and momenta which remain constant in time. So you can say if you want to represent a set of two values which are initially starting at time t naught goes to t1, the information between any two this states transition, it will for each partition at a time t, if p is at time t naught, and information is p t naught, and the another information is at time p prime which is at time t1. So there will be conservation of information in the sense that the map is unique, in the sense that in that phase space the and the information of those position and movement coordinates from one state to another state, if we map them, and so it will be constant. So that gives us, in a sense, in conservation of information, it's I of P T naught, such that I total is equal to I total T naught, which means information is conserved. Now we can have position and momentum. We can have this Boltzmann's So we can talk of now Boltzmann's distributions or Maxwellian wave. So in a given ensemble, where will the total amount of information, where things will equilibrate before the concept of Poincare recurrence states or Maxwell-Lemon, how ideally a Maxwell-Boltzmann distribution will, how things will, what's the, except for the rare fluctuations which can be there, we can say the Maxwell-Boltzmann distribution, Maxwell's distribution, we should say where the classical entropy is maximum. So entropy, however, is except for the Boltzmann constant for I marginal maybe is Ix1 plus Ix2 plus Iz1 Iyx1 sorry Iy1 Iz1 plus Ipx1 Ipx and yn Ipz. So that's it. These are position and momentum coordinates. For marginal distribution, which should tend to be minimum. But this is for marginal distributions. So we are only interested in certain specified class of states in the total ensemble of the states. It will come out to be minimum in that sense, but it will come at the cost of the expense of the total information of the whole state of the system, which is assumed to be maximum. So if total state, for example, and if it is somewhat this part is in a marginal distribution, it's correlated with the rest of the system, then I total can be I total minus I marginal. So this total information remains constant. So one could replace. So one way to define total entropy of the to be negative of the total information, one could replace second law by a law of conservation of total entropy, where yes. So if it's not minimum, so if it doesn't come at the expense of this, so it will come out to be constant. So you could replace the statement of second law that entropy of the system is not increased, it will remain constant. Since it comes out to be minus thing, so this information has to be subtracted from the total system, which equilibrates at some minimum or at some state. So it's compensated by negative correlation entropy. So this is sort of this is not so the aim of this today's class was to become the sort of language we have to set how can relate information vis-a-vis marginal distribution, conditional distribution, and the joint distribution. The joint distribution, you have to have where the parameters may be more than one. So how we can relate a part of state with the rest of the state in that sense. So in the later states, we are going to invoke observer, a quantum mechanical observer, who is trying to identify or filter data or information filter data or information in the entire this system, and then relating that thing with how we can describe a quantum mechanical state. So we'll stop here.